Hi, y'all. Brian Fisher here again with my uh, part 3B of my Path to Faith series. This one, I want to talk about organic chemistry and some physics. So I am going to try to simplify it as much as possible and that'll make it quicker. But I will be using some technical terms, so I hope I don't lose too many people with this one. So I'll just basically start by saying I'm going to focus primarily on visible light and the electromagnetic spectrum, which light is part of. That is just to the left on the spectrum, which would be ultraviolet, which is higher energy than the visible light, and then infrared, which is on the right hand side. So it's lower energy, and if you continue on either side, basically the electromagnetic spectrum is getting lower energy as it goes out to the right. It gets to microwaves, radio waves, and longer. And then on the left-hand side, it basically goes to X-rays, to gamma rays, to cosmic rays. So higher energy. But for this, I just want to focus on these three components, basically the ultraviolet, the visible light spectrum, and then infrared. And so and how that relates to organic chemistry, which is the chemistry of life. Organic chemistry is mainly carbon-carbon chemistry, like bonding atoms together, bonding carbon and oxygen together, and bonding carbon and hydrogen together. And of course, there are many other elements used as building blocks in life. Like sulfur is key, phosphate, nitrogen. So there's like basically probably 1/3 of the periodic table is used to support our life. I don't know that, but it's a significant number of trace elements and things like that are used for us. Like we use molybdenum, which many people can't even say. It's many people just call it Molly. The fascinating part that I mentioned before is that the sun creates this wide range of energy from the fusion of hydrogen to form helium. So basically, two hydrogen atoms fuse to form a helium atom, and the excess energy from that reaction is in the form of electromagnetic energy, and that basically reaches us in the form of light. Light is just one part. Visible light is just one part of the energy that's released from that. So it's a very wide-ranging amount of energy that's released. And our Earth does a spectacular job of filtering out the energy that will not support life, and allowing the energy in that supports life. And I'm just going to go through basically the blocking of the ultraviolet and the infrared, and also just basically how we survive on the energy that gets through. And it's so elegant. It's so elegant. So we basically start with basically chlorophyll, which is in plants. That is as far as I know, like there's other forms of organic, of ways of capturing energy on the earth. There's some really weird bacteria that can use the energy at volcanic like vents in the deep ocean. I think they're called thermophiles. So they have a very, very different life or metabolism. But we're not going to focus on that. That's just a fringe type life form. The vast majority of life is based on plant life. You know, it starts with plants and bacteria that, like, can't remember what they're called, green algae or something like that, which is, it's like a bacteria that can absorb light energy. But I'm just going to focus on plants. And first of all, why are they green? It's because they actually don't absorb green light, they reflect green light. So green light is not what produces or is absorbed by the plant to produce the energy to create the molecules necessary for life. So it's actually the blue and the red light, which are absorbed, which are actually, one is the red is lower energy and the blue is higher energy. So it's funny, there's like this dip in the middle, which is not absorbed, which is the green, and that's why we see green plants. I'm not going to go into the differences. I don't actually understand why there's two different kind of chlorophylls, that one absorbs blue and one absorbs red. But it makes it much more efficient for them to be absorbing two forms of light versus just one in the middle. So in a very succinct, I'm going to try to go through this as quickly as possible because it's quite elaborate, and I'm just going to make a lot of shortcuts. So basically, light is composed of photons. That's the particle which carries the energy of light. So it takes 8 photons to split 2 molecules of water and form one oxygen atom, or sorry, one oxygen molecule, because a molecule of oxygen is 2. It's called a diatomic gas. So basically it's O2. So there's 2 molecules that are comfortable together. A single molecule of oxygen is called a free radical, and it's not happy, and it likes to react with anything around it. So it's very destructive. So we get this O2 molecule, and then we get, it releases hydrogen in the form of just basically protons and electrons. So it splits the hydrogen proton away from its electron. So, and that electron, those freed electrons and that free proton go on to then start the chemical reaction process, the chain reaction, which uses a lot of different enzymes and a lot of different separation, like you need to separate the negative ions from the positive ions, otherwise they would basically just come back together again and form a happy hydrogen. So through this really elegant process, they call it electron chain, you get to the point where you have an excess of hydrogen or protons inside of this cell, and they flow out what's called this thing called ATP synthase, which is adenine triphosphate. So basically, this channel where when the proton flows through this channel from the inside of the cell to the outside of the cell, it changes adenine diphosphate to adenine triphosphate, and it's called ADP and ATP. So, and then ATP becomes it's like the money. It's like the energy exchange. It drives almost all reactions within the body. It then, this ATP is then used in a chemical reaction in carbon, basically in organic chemistry, to make sugars, it basically forms all organic molecules within the body. It is the energy source that the body uses. So the body basically transforms ATP to ADP, very elegantly. So that, in a nutshell, is how how plants basically form sugars, and then sugars, proteins, whatever. Then we consume those nutrients, and then we can have our own way of taking those nutrients and taking ADP and elevating it to ATP, and the cycle continues on within our bodies. It's miraculous. But what's so important about it is it takes this light energy, and which is not strong enough in itself to hurt us. Like, it's not strong enough to break a carbon-carbon or a carbon-oxygen, or like whatever we're made of. Light energy is not strong enough to break those bonds. But chlorophyll is this miraculous structure which is able to capture 8 photons of energy and then convert that into the splitting of water. Like, it's like a step down. It takes 8 photons to split 2 molecules of water. So it's basically a 4-to-1 ratio. That is that whole process is analogous kind of to the way we see as well. Like, the light that comes into our eyes, it doesn't react per se with our carbon. Like, it goes through the same kind of step up process. In order for us to actually see something, we actually have to concentrate the photons first of all, and then they start to set up a chain reaction within our eye. It's kind of like the reverse of photosynthesis, where then we can actually detect whether it was green, red, or blue. And basically we have these 3 different rods. One detects green, one detects red, one detects blue, and we go through this whole processing in our brain to try to figure out what color we're actually looking at. It's so miraculous how it works. But the reality is that the light energy doesn't hurt us. It's lower energy, and it's basically this summation of photons that happens this molecular reaction, which, when you sum it all up, then we can actually detect at an energy level that our brains can understand what we're actually seeing. It's so crazy. Lastly, I just wanted to explain how the Earth's atmosphere is perfectly designed to keep at least the ultraviolet and the infrared from getting down and hurting us. So ultraviolet light does have enough energy to break carbon chemistry, or to break the bonds in carbon chemistry, in organic chemistry. So that's why, like if it's a really hot summer day, some of the sun's energy does get through the ozone layer, which is the primary filter for ultraviolet and higher energy light. So basically, what happens with ozone is called O3. It's 3 oxygen molecules. So, and it's in a thin layer up in the atmosphere. So this ozone layer basically is like if a photon of ultraviolet light hits an ozone molecule, it splits it into two oxygens, an O2 and an O. And an O is not happy alone. It's what's called a free radical. It has an imbalance in its outer in its valence, they call it. So it immediately goes seeking for another molecule to join with. And up in that layer is also O2. So oftentimes this single O will find another O2 molecule and form ozone. So basically the energy, the UV is absorbed by a simple breaking of ozone and then reforming of ozone. And that just happens continuously. The O2 in the atmosphere is far higher in concentration than the O3. So basically, there's an seemingly infinite amount of O2 that's going to feed this, this single O is going to go find an O2 immediately and form another another ozone layer, ozone molecule. So that's how the ultraviolet is filtered out. And the infrared is filtered out by water molecules. If you've ever wondered how your microwave works, it is so infrared waves up to radio waves. So microwaves are in between infrared and radio waves. So microwaves, they energize the hydrogen atoms on water, or on the oxygen in water. So basically, the water's kind of like shaped like a V. So the oxygen's there and the 2 hydrogen molecules stick off. They like start to bend this way, or they go back and forth this way, and that movement causes heat. So basically, all the water molecules in the atmosphere are being bombarded with this infrared energy, and and lower forms of energy, like into the microwave, into the radio wave, and it's basically heating them up. And they eventually, of course, their heat is dissipated out to space, or the heat is transferred into other molecules in the atmosphere, and eventually it's going to drive weather. You know, it's like it's going to cause uh, heat will reach the surface of the planet, and water will in the oceans will warm up and vapor cause evaporation. So in a sense, that's what drives in part weather on Earth. So it's these two very simple reactions in the atmosphere. One of them is a chemical reaction. The other one is just simply a physical phenomena on the with the water molecules, and that is miraculous. It's like when you start to understand the simple physics of the Earth's atmosphere, and how perfect it works with the life on Earth. Again, it's just an absolute miracle. So that's the end of this part, and next one I will get more into the Earth's other the way the Earth is situated in the solar system, the sun, how it itself kind of creates the safe zone in our solar system as well, and the Earth's magnetic field, which again does an amazing job of absorbing higher energy, like electromagnetic energy. So that's it for now. I hope this was helpful and not too confusing. Bye for now.